Good day, everyone. I am Akintunde Makinde. I'm working on how well do CMIP6 models simulate the influence of West African Westerly Jet on Sahel precipitation. The Sahel, a semi-arid region in West Africa, forms a transition zone between the arid Sahara Desert to the north and the belt of savanna to the south. 85% of the Saharan population depends on rain-fed agriculture, which contributes at least 35% to the national GDP in the region. Studies have shown that rainfall variability in the Sahel fuels extreme events like floods and drought, which causes degradation of the environment, damage water resources, induce disease epidemics like malaria and meningitis in the region, and also destroy agricultural products such as crops and pasture. Despite the impact of rainfall variability in the Sahel, simulation and prediction of rainfall variability in Sahel still remains a big challenge for global climate model. Any improvement in the simulation and prediction of rainfall variability over the region could go a long way to reduce the impact of rainfall variability over the socio-economic development in the Sahel. However, such improvement requires understanding of how contemporary climate models represent the rainfall producing futures over Sahel and over West Africa at large. West African Westerly Jet has been identified as one of the atmospheric futures that modulate precipitation over the Sahel. West African Westerly Jet is a low-level jet located at the coast of West Africa between 8 and 12 degrees north at 925 hectopascal. The jet develops in June, accelerates in July, and reach a maximum in August. Poole and Cook in 2010 studied the dynamics of West African Westerly Jet, and they found that the jet has a strong positive correlation with precipitation over the Sahel. It is therefore important to evaluate how contemporary climate models, such as the Coupled Model Intercomprehensive Project 6 or CMIP6, represent West Africa Westerly Jet and its influence over precipitation in the Sahel. For this study, we seek to understand how CMIP6 models simulate the climatological structure, the strength, and the position of West Africa Westerly Jet. We want to know how the models capture the correlation between the West Africa Westerly Jet and the precipitation over West Africa. And lastly, we want to understand how the model represents the moisture transport by West Africa Westerly Jet over West Africa. For this study, we extracted monthly variables from 26 data sets from Coupled Model Intercomprehensive Project Phase 6, that's CMIP6 models. First of all, we want to understand how CMIP6 models simulate the climatological structure and strength and the position of West Africa Westerly Jet. We start by investigating the temporal, the spatial, and the vertical structure of the jet in the model. For the temporal structure of the model, we investigate the magnitude and the annual cycle of West Africa Westerly Jet climatology from 1980 to 2014 in the model. We define a threshold of 4 meters per second represented by the thick dashed black line to determine the maturity of the jet. Above this threshold, we say the jet has reached maturity and accelerates to maximum in August. The reanalysis represented by the thick black solid line showed the annual cycle of the jet with a maximum course speed of 5 meters per second in August. Majority of the models capture the annual cycle of the jet as seen in the reanalysis. However, the jet develops too fast and too strong in majority of the model, about 23 of the models. For example, the BCC models, in the BCC models, the jet develops in March and reach a maximum intensity of 8.5 meters per second. Nevertheless, 4 of the models fail to simulate the temporal structure of the jet. Only 3 of the models perform best. Secondly, for the spatial structure of West African Westerly Jet in the model, we investigate the spatial distribution of West African Westerly Jet climatology from 1980 to 2014 with the associated ITCZ. The contour lines represent geopotential height at 925. In the reanalysis shown in panel 1, the jet is located off the coast of West Africa and spans from 6 to 12 degrees north and from 15 to 35 degrees west. Majority of the models capture the spatial structure of the jet as shown in the reanalysis. However, 9 of the models, as shown by the correlation values at the bottom left of each panel, disagrees with the spatial pattern in the reanalysis. For example, the CAMS model with a negative correlation of 0.2 locates the jet at 4 to 9 degrees north and 10 to 30 degrees west. Also, most of the models overestimate the area coverage and the core strength of the jet. Again, the MRI model underestimates the area coverage and the core strength of the jet. Thirdly, we investigate the latitude I cross section of West Africa Westerly jets. In the era 5, the jet extends from surface to 750 HPA, and the jet core is located at 925. Africa Westerly Jet is located to the north of West Africa Westerly Jet. This northward displacement of Africa Westerly Jet is in agreement with the findings of Grist and Nicholson 2001 that equatorial westerlies, including West Africa Westerly Jet, displace Africa Westerly Jet northward and modulate its internal variability. Most of the model capture the vertical structure of the jet and the associated northward shift of Africa Westerly Jet as shown in the reanalysis with different capabilities, except the MRI models, which shows the jet core, at 1,000 hectopascal. Secondly, we seek to know how the model capture the correlation between West Africa Westerly Jet and precipitation over West Africa. We investigate the spatial distribution of temporal correlation between West Africa Westerly Jet and precipitation over West Africa. The observation, that is the era 5 with cool precipitation, shows a strong positive correlation between West Africa Westerly Jet and precipitation over West Africa with a peak correlation value of 0.8, which is higher than the one reported by Poo and Cook 2012. Majority of the model capture the positive correlation between the jet and precipitation. However, only 7 of the models perform best by showing a comparable pattern with the observation as indicated by the correlation values at the bottom left of each panel. Lastly, we investigate how the models represent the moisture transport by West African Westerly Jet over West Africa. We look at the difference of the composite of precipitation, temperature, and moisture flux anomalies during the positive and the negative mode of West Africa Westerly Jet from 1980 to 2014. During the positive phase of West Africa Westerly Jet, there is a net transport of moisture eastward into the subcontinent within the 5 to 10 degree north band, and a more transport of moisture northeastward from the band into the Sahel, north of 10 knots. This suggests that, firstly, the stronger the West Africa Westerly Jet, the more moisture is transported eastward into the continent. Secondly, the increase in the eastward transport of moisture by West Africa Westerly Jet provides more moisture for the northeastward transport of moisture by the monsoon flow. This increase in the moisture transport into the subcontinent increases the precipitation over the region. Majority of the model capture the 2 distinct increases in the moisture transport by West Africa Westerly Jet. However, few of the model fails to capture it. For example, the E3SC model. While some of the models that capture the 2 distinct increases in the moisture transport by the jet does not translate the moisture to a commensurable increase in precipitation north of 10 degrees north, as shown in the observation. In summary, most of the CMIP6 models reproduce the temporal and vertical structure of the jet, but the jet develops too fast and too strong in majority of the model, with reference to era 5 results. Only 3 models perform best. More than 38% of the models disagree with era 5 on the spatial structure of the jet. Only few of the models capture the correlation between the jet and the precipitation over Africa. Few of the CMIP6 models do not capture the 2 distinct increases in the moisture transport during the stronger West Africa Westerly Jet years. Some of those models that capture the 2 increases do not translate the increase in the moisture transport to a commensurable increase in precipitation north of 10 degrees north. Thank you.